Hello, this is lesson 5.3b, Logarithms and Logarithmic Functions. This is a continuation of 5.3a, and in 5.3a we learned how to change from a logarithmic to exponential form and vice versa. So in this lesson, we're going to talk a little bit about inverses, how they undo each other, and how to graph logarithms. Okay, so before I talk about this next part, when you find if a function is an inverse of another function, the input is going to be the output. So if you plug one into the other and vice versa, you should just get x. That should be your answer. So in this case, if I take log base b of x, see that x right there? If I replace it with b of x, it's going to be equal to x. So let me show you what I'm talking about. So log base b, now there used to be an x here. What they did is they substituted b of x. These are inverses of each other, so it cancels out. Notice how the base and the big base here, they're the same. So as long as they're the same, then that's just going to give you the exponent. So if you see this pattern right here, all you have to do is write the exponent. That's the inverse property. Vice versa, log base b of x, if you take that and replace it into the x of your exponential function, see how your bases are still the same, also going to be equal to x. So if you just notice the pattern, you'll realize that the exponent itself is going to be the answer. So let's do a couple of examples. I'm going to do these two on the top, and then you're going to do these two on the bottom on your own, except for this one's just a little bit more difficult, but we'll see if you can do it on your own anyway. All right, this one, if you look at it, you can't really tell what the base is on the logarithm. Remember, if you can't see the base on the logarithm, it is a base 10 because that is a common log. That looks very much like this situation right here. So if I have the same, this is the same as this base. So if I just cancel that out, the exponent is the answer, and it should just be 4. Okay, over here, that looks very much like this situation over here. If you see that this base is the same as this base, which means that your exponent is the answer. So the bases undo each other because they are inverse properties. So I want you to just kind of play around a little bit, see if you can do this one and the more complicated one. So just pause the video and see if you can figure it out, and then unpause it when you're ready to see the answers. All right, this one's very much like the one above it. You cannot see the base here, but this is a natural log, and the base of a natural log is e. These two are the same base. If they're the same base, this means that they are opposites each other, and your answer will be 18. Over here, the problem is that the 5 does not match the 25. So what you have to do is you have to rewrite 25 in such a way, and that's not it because this is not the same, in such a way that it will be equivalent, but it's not going to be exactly the same. So 5 is not 25, but 5 squared is 25. So they are equivalent. You notice that this 5 and this 5 are the same. That leaves us our exponent, and our exponent is just 2x. Okay, now when we're talking about your end of course or your benchmarks, these properties aren't as important, but they will, and they can show up on your ACT. So I wanted you to see that just to make sure you have seen it before. Now we're going to find the inverse of the function. These aren't the easiest, but I did write down exactly the steps of any inverse. What you're going to do is you're going to rewrite f of x as y, and we've done that before, so let's do that in this first example. So I'm going to write y equals 6 to the power of x. So we've done that. We've also done step 2. We have swapped the x and the y variables. So if you want to start the process of finding an inverse, you're going to swap variables. I like to change the colors to indicate that is now my inverse. Here's the deal. This looks a little bit weird, okay? What you're supposed to do is you're supposed to solve for y. That is the rule for any inverse. But you really can't solve for y, so you're kind of stuck. Now, in lesson 5.3a, we learned how to change an exponent to a logarithm. Since we're stuck, we are going to change. So we're going to change this to a logarithm. Okay, now if you can't remember to do that, remember that this is your base. So as you write your log, you're going to say log base 6. Okay, and it's always going to be 6 of this x right here. So you're going to work in that circular motion. So 6 of x equals y. Did I just solve for y? I did. And all I had to do was just rearrange it. So I went 6 to the power of x is equal to y. Because remember, it's always equal to your exponent in the exponential form. Okay? So all you have to do now is change it into inverse function notation. Okay, on to the next one. We are going to do the same steps. We're going to change f of x into y. And then we're going to swap our x and our y. So this is now x, and this is y. Here's the thing. We don't know how to solve this. We are stuck. And when you are stuck, what you can do is you can change it into its other form. This is logarithmic form. What is the base of this logarithm? This is a natural log. The base of any natural log is base e. So you're going to write e to the power of x is equal to y plus 3. Now you got to clean it up a little bit. It has to be equal to y, so you're going to subtract 3. So final answer is going to be e to the power of x minus 3. Change this y back into function notation. Now I understand that that's only 2 examples, but if you feel like you can tackle the last 2, go ahead and do that. If not, just keep playing the video and let's see if you got everything right. Okay, so this one's just like the one above it. Let's go ahead and change it into y instead of f of x, and then we're going to swap the x and the y variables. That is now the inverse. I don't know how to get y by itself, but I do know how to change it to a different form. This is an exponential form, and we want to change this into logarithmic form. So all I do is take the base. This is base 9, so I'm going to say log base 9 of x is equal to y. And then you just need to simply change that y back into inverse notation. So that one's not too bad. Just remember that when you get stuck, change it to a different form and see if that helps you. So this was also a natural log. Let me get back to it. Here it is. So we're going to start out with y. Then we're going to start our inverse notation. Okay, swapping the x and the y variables, and then we have to realize that that has a base e. So if I want to write it in exponential form, I'm going to say e to the power of x is equal to y plus 6. Like I did the one above it, you have to subtract 6, so you have to get the y by itself. You need to change the y back into, oops, I forgot the minus 6, and then change the y back into inverse notation. All done. All right, so now we're in the graphing section. And then just kind of the general rule for any inverse, it always reflects over y equals x. That's that dotted line right here. The log base b of x is going to be the inverse of b to the power of x. That's at the very beginning of your notes. Do you see how they reflect over this dotted line right here? Same thing over here. This one is b to the power of x. And it's also log base b of x. Now they look different, and they're, ooh, that was terrible. They look different because the base is either greater than 1. So if your base is greater than 1, which means like 2 to the power of x, it means it's going to grow. We talked about that. So if your base is greater than 1, it's going to grow. If your base is between 0 and 1, it's going to decay. That's why the blue line is decaying, it's decreasing over time. But they are still reflective over that y equals x dotted line. You do need to understand that you have an asymptote that is a vertical asymptote, okay? It's vertical, it's not horizontal. You notice this blue line right here. Let me use orange. This blue line gets closer to the x-axis, but it never touches it. It gets closer to it. That is y equals 0. Inverses is going to swap. So instead of y equals 0, it's going to wind up being x equals 0. So let's focus on, let me get rid of everything. Let's focus on the red line. Now I'm going to change it to green this time. So the red line, see how the red line touches the x-axis? It's not a big deal, okay? What it's going to do is it's getting closer to the y-axis. See this right here? And it looks like it's touching it. It doesn't. Remember, you can zoom in and it won't touch it. It is equal to 0. The x is equal to 0. You need to know that. So if it's exponential, it gets closer to here. If it's logarithmic, it gets closer to the vertical line, okay? X equals 0. Please highlight that, circle that. It's very important. Same thing, whether it's a growth or a decay. So if it's the inverse of a growth, it's going to do this. It's going to increase over time. If it's the inverse of a decay, it's still going to decrease. So it kind of messes with your head a little bit, but it's still going to have that same asymptote right here. It's getting closer and closer and closer. Now, if you are in honors, we are going to talk about the end behavior and how that changes everything. But everybody needs to know how to write down the domain and the range. So when we talk about domain and range, where did it go? When we talk about domain and range, we're only looking at the red curve here. That is the logarithm, okay? Let me highlight that for you. So we're focusing on this right here. What is the domain of that red line? Now it gets closer to 0, but it doesn't touch it. So that means it's got a boundary at 0, but it doesn't touch. So you have to use parentheses. And then it goes all the way to positive infinity. It keeps getting bigger and bigger and bigger. So that's one way to write it. Or you can just simply say that x is going to be always bigger than 0. That's your domain. The range, on the other hand, it starts all the way down here. It's negative infinity. So negative infinity, and what's the highest point it's going to be? Well, it doesn't really have a high point. It goes all the way to positive infinity. So you don't have any limitations at all. It keeps going down and it keeps going up. So this is going to be all real numbers. And the good news, if you look on the other side, the range is going to also be the same. It goes up forever and it goes to the right forever. It's going to have all real numbers. It also goes down, sorry, I said range. It goes up and then it goes down forever, so it's also all real numbers. Now the domain changes. Okay, once again, we're focusing only on this red curve. The domain, I lied, it does not change, does it? It starts at 0, continues to the right. Okay, so you can write it this way, or you can just say x is going to be greater than 0. So logarithmics, when they're in their just kind of base form, parent functions, that's going to be your description for your domain and range, and your asymptote is going to be x is equal to 0. So make sure that you write that in there somewhere. Okay, very important. If you are honors, let's talk about end behavior. If you're not honors, you can go ahead and fast forward through this section, or unless you're just curious and you want to know how to do the end behavior. So in the past, we have always had as x approaches positive infinity and as x approaches negative infinity. We actually cannot do that. We can't do that because our domain is limited. The domain actually does not approach negative infinity. It doesn't. So it actually approaches 0. It gets closer to 0. Does it get to 0? No. But as it approaches 0, that's what it does. So as x approaches 0, the y values go down. So it'd be negative infinity. But as x grows, as x goes to the right, it continues to increase. So it goes to the right and it increases. So it'll be positive infinity. Now over here, the end behavior, it's going to start out the same way as it goes to positive infinity and as it approaches 0, because it does not go to negative infinity. So as it approaches 0, it does not aim down, it actually goes up. So if it's going up, your y is going to go to positive infinity. And as it grows this direction, as it goes to the right, it also goes down, decreasing. So y will approach negative infinity. All right, on to the last bit. We are going to be using Desmos to graph these logarithms. Just make sure if you have any kind of translation to the left or to the right, that can change your equation of the asymptote. And if I remember my translations, this is going to actually mess with it a little bit here. This one doesn't have anything. That looks like it's going to make this logarithm go to the right. No. It's going to make it go to the left 3. So we're going to have to be really careful when we graph it. Here's the good news. When you graph it, all you have to do is just make sure that you're looking for key features of the graph, like where's the asymptote, where are your intercepts. So I'm going to go ahead and type in f of x is equal to log. How do we type in a base other than 10? We hit shift dash. Okay, and then hit the right arrow to get out of it, and then we're going to type in x plus 3. There we go. So kind of key notes right here. It's going to cross the y-axis at -2, the x-axis at +1, and look at where it almost touches. It looks like it really does touch this line right here. This is x equals -3. If you're not sure, you can just type in x equals -3 and it will pop up for you. So see, that is exactly what we're looking for. Now remember, our basic logarithms, our exponent, our asymptote is at 0. But since it shifted to the left 3, yeah, so I would confirm that if I were you. So let's go back over and we're going to make a little sketch. So I'm going to go ahead and do -1, -2, -3. And say this is x equals -3. That's my asymptote. And I'm going to say that it hits here on the x-axis at -2, and it hits on the y-axis at 1, and then I'm going to show it its basic like shape right here. There we go. That's all you have to do. And if you want to go ahead and just take it a step further and write down the domain is going to be greater than -3 this time because it shifted to the left. And then your range is still going to be all real numbers. All right, go ahead and pause the video. I want you to graph this one. Don't worry about the fraction. Desmos will work it out. Actually, wait, will Desmos work this one out? We're going to figure it out. All right, so if you just navigate on to Desmos, we're going to type in log base 1/2. So I'm going to delete underscore. Now, if I try to type in 1/2, so 1 divided by 2, that is not at all, it's not going to let you do anything. It's not going to let you do a fraction base. So what you're going to have to do is change 1/2 to 0.5. It will allow you to do that. So 1/2 is 0.5, and then I need to find x. So see, it didn't have any translations to the left or the right, so my asymptote is still at 0. And I only have an intercept here at 1. Now it looks like you might have a horizontal asymptote. You don't. It is going to continue to decrease further and further. So let's go back over to our notes and sketch this real quick. This one's a little bit harder to show. So x is equal to 0 is my asymptote, and it looks like I hit at +1. There we go. That's our basic shape. Okay, if you are a regular student, you can go ahead and stop the video and start working on a practice. But if you're honors, I want you to answer this last question. How can you tell if this graph increases or decreases from left to right without using technology? So think on that for just a second and then unpause to hear the answer. Okay, so the answer is assuming that there's no like reflections, okay? So that's kind of out. Assuming there's no reflections over the x or the y axis, you can tell by looking at the base. So if you know that you have a base that is greater than 1, you know that it is going to increase. So see, log base 3 is increasing. And if you know that your base is between 0 and 1, it is going to decrease. It's because it is, if you realize that that sounds a lot like exponential bases, it's because they are related. So let's write that down. Oh, and I shouldn't say 0, it should say 1. So if the base is greater than 1, it will increase. And if the base is between 0 and 1, it will decrease. So very much like the exponential form of the same base. And that is it. So good luck with your practice. Let me know if you have any questions.